Okay, let's start the session today. We discussed about the unit cell, right? So you can remember about the unit cell, which is the smallest repeatable unit in the lattice, right? So if you don't hear me properly, please let me know, and also please input your registration numbers in the chat box to mark the registration. Sorry, mark the attendance. Okay. There are lattice points, right? So lattice points means edges and center points. Okay, these are the lattice points, and connections to these is a feature of the unit cell. So this is repeating. So this should be, you should be able to repeat it three-dimensionally. Okay, not just in one dimension. It should be three-dimensional stacking. Okay, so like this, the unit cell should be, you should be able to uh, fit it without any spaces in between. You cannot have any spaces in between. Okay, there shouldn't be any spaces in between, right? So by this process, with combination of unit cells, you can make the crystal lattice. Okay, then only you prepare the lattice, right? So when you interconnect this one with different unit cells, we call it motif. Okay, so motif is kind of a basis for the lattice, right? Sometimes it's exactly the lattice, but sometimes people want to make it like a framework. Okay, so it's very difficult for me to write with this trackpad, but I'm trying anyway, right? Motif. Okay, so the lattice and motif is important. It shows the systematic arrangement of the unit cell. Okay, right. So we again mentioned about the shapes and sizes, the importance of unit cells, where we quantitatively describe the crystal. Okay, to describe the crystal quantitatively, we need to know about the shapes and uh, sizes of unit cells. That's important. And also location of the lattice points is also important, because by repetition of this unit cell, for example, if in any case, if you want to move this unit cell into another place, right? And the relative distance between the respective lattice points should not be changed, right? Even though you moved it uh, in a unit of uh, d, for example, right? At the new position also, this d should be constant. Okay, so these are important. That means the shape and the relative distance cannot be changed. The distance cannot, relative distance cannot be changed in a unit cell. Okay, right. So these are some important points that we have to consider about quantitative description of crystals, right? Unit cell shape and size is important, right? And also the location of the lattice points. That means the relative positioning of these lattice points is also important. These two aspects we call into terminologies, separate terminologies. One is point symmetry and the other one is transitional symmetry. These two symmetric uh, points, I mean, the aspects of this unit cell arrangement is described in terms of symmetry, right? Because this is talking about the symmetry, because if you change this position, if you distort the crystal, that means your crystal does not have a symmetric shape, right? So geometrically, it should be symmetric, right? So for that, these shape and size and location of lattice points are very important. Uh, for example, uh, when we stack these unit cells, right, one by one, right? So you have one unit cell, the second one, third one, and fourth one, right? So likewise, if you stack them up, right, together, uh, there shouldn't be spaces in between, I said, right? You can't have spaces in between, right? So a cube is a perfect stacking unit cell. You can stack them without any problem, right? So this cube gives you zeros space, and it fits very well together, right? So it makes a perfect crystal. But if you take some shapes like a pentagon, right? If you take some shapes like pentagon, what happens? When you take the pentagons, what happens? You cannot stack them in a proper way, right? Whatever the way you try to stack them, you will end up with some space in between, right? Some space is there, so it's not perfect type of stacking. So therefore, some restrictions are there for unit cells. Some restrictions are there when you choose the unit cell. Uh, So geometry is important for crystals. So in natural crystals, that's why any shape cannot be. I mean, you don't see any. You don't see many crystals in any with any shape, right? Only some defined shapes only you find. That means only with some symmetry is possible will naturally form crystalline shapes, right? Otherwise, you would see infinite number of shapes for crystals, but you don't see that, right? For example, you will learn in the future about the crystal system, number of crystal systems, and their subgroups like that, right? So you have only seven main crystal systems. That's all dependent on the shapes, right? So this is very important because this describes about the symmetry, right? So this classification is also based on the symmetry because of that. Right. So it's kind of a rule, mathematical rule, symmetry. It's a mathematical rule because if you define a center point for a crystal, not a crystal, anything, right? So if you have two objects like this, right? You have two objects. One is a square, and the other one is a slightly distorted square. So if you take the distance from the center to these points, to the edges, right? In the first case here, the distances are different because you see some kind of distortion here. But in this case, it gives you all equal lengths. So that means you can have a symmetric plane there, right? In the previous case, even though you try to make it a half, along a plane, whatever the plane, you don't see any symmetry. But here, you can expect a symmetry. So therefore, it's kind of a set of mathematical rule that describe the shape of an object, whether it is symmetrical or not. So what is the object which has a perfect symmetry? Cube is also having a near perfect symmetry, but some distortions might cause the cube to have some differences in the symmetry. But if you take a sphere, right? If you take a sphere, it's all over the directions, any direction if you take, right? This direction, this direction, or this direction, or infinite number of directions which you have along in a sphere, all are symmetric, perfect symmetry, right? So this is the only object that you have a symmetry as a perfect uh, object, right? So there are infinite number of planes which you can describe as a symmetric planes, all passes through the center, right? All passes through the center point. And also, if you even if you rotate this one, right? Even if you rotate this sphere in different directions, whatever the direction that you want to rotate it, right? Still, you can preserve this symmetry. Whatever the angle you rotate and see, it won't change the shape, right? But in non-symmetrical objects, if you rotate, for example, if you rotate this one, if you rotate this one and see at different angles, you will see different shapes. Sometimes you see like this, right? Sometimes you will see something like this, right? So likewise, you see different shapes when you rotate. That means you can't preserve the symmetry there, right? So planes of symmetry and rotational axes are important for defining crystals, right? Some crystals, for example, if it is a ball-like thing, if it's a sphere, you will see infinite number of rotational axes as well as infinite number of symmetry planes. But all crystals don't have this feature because they are not spherical. All are not spherical, right? If something is spherical, then definitely you will have that kind of symmetry, right? So cube and sphere are you can take them as perfect symmetrical objects, right? Uh, Being the sphere is 100% symmetrical, but the cube is also 100%, but still there can be some changes to its symmetry, which you may learn in advanced crystallography, but not at the undergraduate level. Okay, right. So this is what you expect from symmetry, because you need infinite number of planes, right? You need infinite number of planes uh, and infinite number of rotational axes in a sphere, right? Of course, for a cube also, you can have a similar type of geometrical planes and axes. But for most of the crystals, you can have some limited number of symmetry axes and symmetrical planes. So depending on that, these crystals are categorized. These crystals are categorized into groups. So one group can have different set of crystals according to be crystallized along with that features consistent with that group. Uh, so that makes different crystal types in the nature, right? So these are not really not really uh, artificial thing. Natural crystallization also this happens. These rules are followed by the nature. Okay, right. So we'll see what crystal's space group defines, right? So actually the symmetry, is derived by a periodic pattern, right? Symmetry is defined by periodic pattern of arrangement of repeating unit cells, right? Unit cells, a set of unit cells when they are in a kind of network like stacked together. You can call it a motif, as I said before, right? A collection, right? So this repeated motif will tell you about the symmetry of the crystal. So we call these symmetric mechanisms of having these symmetries as symmetric operations or symmetry operations, right? So some limited symmetry operations are allowed by a given pattern. But if it is a sphere, unlimited symmetry operations are there. That means an infinite number of symmetry planes and infinite number of rotational axes, right? So these all together define a space group, right? All these atoms or ions, they define a space group based on their symmetries. Right. So, uh, suppose you have a pattern like this here. right? You have a pattern, and you make this pattern rotated by 90 degree, right? You rotate it by 90 degree about the center point, right? So you have a center point, and about the center point, you rotate it by 90 degree. So what will happen? All are cubes, right? You have all are, I mean, the unit cells all are cubes. So that means the entire shape is also cubic shape, right? So whenever you rotate this in 90 degrees, will you see any change? No. So this pattern will be unchanged as a result of this operation, right? So we call this operation maps the pattern itself. The operation maps the pattern itself. That means it makes an identical shape again after rotation. So that does not mean the symmetry is distorted, right? So we call it mapping itself, the pattern itself into itself. Okay. So this is one feature of a space group, and another possibility is you try to move these unit cells together as a system uh, from, I mean, to some distance. For example, D. Let's say this is moved a little bit by a length of D, right? So what will happen? It after D distance, it will again appear as the same pattern, right? So it will appear as the same pattern even though you uh, move it any direction, right? Maybe this direction or even uh, offset in a oblique direction like this, right? It won't change. So the shifting or movement, or we call translation, does not change the shape. Geometrical shape is not distorted, right? So these are the symmetry operations that we can do for a crystal, and these operations will not change their symmetry. So we call the space group. This is the space group is not distorted by its symmetric operations. That means rotation or translation, right? So we call the pattern symmetry uh, as having rotational symmetry as well as translational symmetry. Both symmetries are there. Some patterns might have only one of these type of symmetries. Okay, so uh, actually the space group defines its symmetry, because you know being this is the space group, you tried showing rotation as well as you tried showing translation, right, in any direction, but still it did not change its pattern. So that means the space group defines a crystal's symmetry, right? So each crystal has its own space group, right? Each crystal has its own shape, own space group, which is which is a result of or kind of a feature of its internal structure, right? Its internal structure defines this symmetry, right? So that's how the unit cells are stacked together. So the symmetry is important to define the space group, right? Some crystals can have space groups which have only rotational symmetry, whereas some groups can have only translational symmetry. But some groups, some crystal space groups can define both type of symmetries like cubic systems. So this is also important when you consider about the symmetries. Right. So translational symmetry, as we described before, it's a kind of it's a kind of uh, geometrical rearrangement of the crystal, and the point symmetry that was equivalent to the rotation line, because we are rotating the crystal or the object along an axis, right? Along an axis. So it's along a point we are rotating. So this is a point symmetry. Rotational symmetry defines always a point symmetry, right? The translational symmetry means it's always movement in relation to one direction. So it's a kind of a vector type of symmetry. So shifting movements are the translational movements. If you don't see any difference, right? For example, even here, right? This is a SCM image of crystal. So you can make it moved to a constant distance, right? It cannot be the same distance in every crystal. It may be depending on the crystal type, because d is not always the same distance. Any distance will not define translational symmetry for all the crystals, right? But for cubic type or spherical types, any distance is okay, but for all the crystals it is not like that, right? For example, if you want to repeat this part, right, if you want to translate it here to here, it won't make a symmetrical shape, right? It's different. So therefore you have to take the real or correct distance to make it a translation, right? So but the thing is this is atomic scale, right? This is atomic scale. uh, so you can't see it macroscopically, right? Because they are in angstrom. You know angstrom, this unit, angstrom. Angstrom means it's a unit of measurement of length in crystals, right? Angstroms. So very, very, very little distance, uh, very micrometer scale distance, very little distance, right? So this is very important, right? For example, that this is a cordierite crystal, right? A mineral called cordierite. So you want to move it, then you have to move it up to here. Then you can see a translational symmetry there for the crystal, right? So macroscopically available symmetries are there for big crystals, but if you observe it in atomic scale under SCM or some other technique, you might not see it uh, optically, right? Because it's the length is very, very small. But for large crystals, you can see it clearly. Do you have any questions? Okay, there are some macroscopically available symmetric operations, right? Macroscopically available symmetric operations, which we can define in other some other terms. Okay, so we have to consider uh, a respective point of crystal. For example, if you have a crystal again, right, symmetric crystal, and if you take this point after the operation, also you should have the same configuration where you see the same point with relative to the other points at a same distance, at a given distance. So if originally it was like this, after the symmetric operation also it should define the same distance. That means that point should not have been changed or gone to a different place, right? So there are several types of operations you can have. uh, for that we can see if you take a symmetric crystal for example like this, and you make kind of reflection, right? For example, if this crystal was like this, uh, right, with arrow heading to the upward direction, right? But after the operation, for example, if you make it inverse, I mean, if you want to make it an inverted crystal, you put it upside down, right? You put it upside down, then what happens? The arrow will be bottom, but all the features, geometrical features, lengths and all will be constant or same, right? No difference. So this type of symmetry operation is also there. So that means you can put something upside down and then look at the symmetry, right? So that sort of a symmetry is called an inversion, right? Inversion of a symmetry, right? Inversion of a symmetry. Right? So this can be like if you have a crystal like this, and maybe you can turn it like this also, right? So in that case, if you define a central point here, the distance from here to the corner should be equal to the distance from here to here, right? So this is a kind of a inversion. And the other one, that is the first type, and there is another one that's called mirror symmetry that you know very well, right? So if you have a crystal and if you define a plane, if you define a plane in the crystal and you can see the identical shape, you should see the identical shape in that crystal after you observe along. I mean, if you make it into two halves, then still you see the identical shape. So it's exactly like a mirror, right? So we call it mirror plane. And the symmetry is called the mirror symmetry, right? This is not available for all the crystals, right? For example, if we had a crystal like this, you may not have a mirror plane, right? You can't make a mirror plane like this or any other direction, right? So mirror plane, if you can decide a mirror plane along the crystal, then you can call that crystal has a mirror symmetry also, right? So this is another type of symmetry that you can expect in a crystal. The other one is the rotational symmetry that we already discussed, right? You can rotate the crystal along an axis, right? You can rotate that along an imaginary axis, right? That is rotational symmetry. Whatever the angle you rotate, if the symmetry is same, then you can say that it has an infinite number of rotational symmetries. But some crystals has only I mean, give you the same symmetrical shape at some intervals only, right? For example, 60-degree rotation, you can see the same shape, and another 60 degree, you get the shape again, right? But maybe if you rotate it 75, then you see a different shape, right? So that means rotational symmetry is dependent on each and every crystal system except for cubic and uh, spherical objects, right? Rotational symmetry. And a combination of rotation and inversion is called roto-inversion. Combination of rotation and inversion. So once you rotate and then you make it inversion, upside down, right? So in that case also you will see uh, kind of a symmetric operation, right? That is another symmetric operation which you will have as roto inversion, right? Just inversion will not make the same shape, but roto inversion will make the same shape for some crystals. So roto inversion is not available for all the crystal systems, all the crystals, for some crystals only, right? We'll see some examples later. Right. So I will show you about this inversion again, right, with some examples uh, where you see the say this is the original status, number one's original status, and number two is the latter status. So the latter state is here, and the original state is here. So some after some symmetric operation, if you just look at uh, the distances from a central point, right? This is an arbitrary central point, imaginary one, but you measure the distances from here to here and from corresponding opposite direction, and from here and from here, right? From here and from here, also from here and from here, right? So what happens there? It's kind of a projection. You can call it a projection also. A projection of this particular point on this second status is here, right? So you have projected it to here, and you have projected this point here. You have projected this point here. So this is what you call the inversion, right? So this is uh, it's a kind of a inversion where you can see the distance from a central point is equal, right? So this is inversion, right? So this point, the central point, you call it center of symmetry. The central point from where you measure the distance can be called the center of symmetry. So center of symmetry is not always available inside the object itself. Remember, it's something like the center of gravity, right? In physics, you remember, always the center of gravity is not associated within the object itself, right? Sometimes it's available outside the object, like that, right? So this is the center of symmetry, yeah, after the inversion. So it's a kind of a projection, okay? So the same distance is important, right? At the same distance, you should be able to locate the corresponding point after the operation. So this is just an operation. The object is just kind of inverted to some other direction where you measure the distance from a central point. Right. The second one, the mirror symmetry, right? This one, the mirror symmetry is always associated with exactly you are placing a mirror, right? So these are for examples. Actually, we take some examples from outside the crystals because for us to clearly understand this one, right? Even this one, right? You can make construct a crystal there, right? So like this, you can construct sorry, you can construct the crystal, right? There you observe one face here and corresponding inverted face another uh, on the other side, right? In a three-dimensional crystal, right? This is not just the planar things we are talking about. These are crystals we are talking about, three-dimensional things, right? So if you find a similar plane which is inverted in a crystal, right, uh, in the opposite side, then you can take it as a inversion, the symmetry, inversion symmetry of that crystal, right? All crystals will not give you the same type of symmetrical features, and this is different from the reflection also. Mirror symmetry is another thing, right? So, for example, if you put a mirror here, will you see the same feature, mirror symmetry? So if you see a mirror, then you should see something like this, right? For this one, right? So this is different. This is not mirror. This inversion, right? Now the mirror is here. You have one side like this, for example, and if you put a mirror, then you should see something like this. Okay? So this is mirror. So you have a mirror plane there, and you can have a mirror plane in this direction also, and in this direction also here. So if you put two mirror planes, for example, in one direction here and the other direction the other way. So you in this way you call two operations consequently, right? So first first operation is here and the second operation is here. Okay, so there are two symmetric operations which make a different shape, right? For example, this shape is the opposite of it after reflection by a mirror. But if you put another mirror here in this way, you see similar type of feature, but still it's a mirror after the mirror operation, right? So remember, some cases you can some crystals or some suppose this is a crystal, right? This is valid for the crystals also. So two consecutive operations will give you uh, entirely different picture at the end, but intermediate or the uh, in between operations, for example here, this is an in between operation, right? Uh, there you don't see the difference even though it's after the reflection, right? It's because of the shape of this particular crystal. It's not the shape of this crystal, right? This crystal is now different shape. That one will give you the identical shape after the mirror operation, depending on the plane, depending on the symmetry plane. So in a three-dimensional crystal, you have to find out uh, the real plane where you can define some symmetry, right? So these mirror planes are hidden in crystals. So you have to look into these mirror planes in a crystal. Okay, then you can find whether what sort of symmetry is there with that particular crystal, right? So okay, you can take a good example with the people, right? Vertebrates, right? They have a mirror symmetry, right? So biology people, you know that mirror symmetry. So what do you call this mirror symmetry in biology? It's called bilateral symmetry, right? Bilateral symmetry. Okay. Now we'll see the rotation. What happens after the rotation? The third one, this one, right? Rotation. So what will happen after the rotation? So suppose you have a shape here, six, and three slashes, percentage mark is there in between, right? But you just take, yeah, you rotate this one anyway. Anyway, you take this and rotate this unit, right? Rotate it like this in 180 degree. You rotate it by 180 degree. Then what happens? It's entirely uh, other way around, right? Opposite time, right? But if you rotate it 90 degree, you see a different thing, which is not symmetrical, right? So you can produce an inversion type symmetry by rotation also in some cases, right? Anyway, these are rotational symmetry. And if you rotate this triangle like this by 60 degree, if you rotate this angle 60 degree of this triangle, why I select 60? It's 60 here, right? This is a this is a triangle, has equal sides and equal angles, right? So every 60 degree will give you the identical shape, right? Every 60 degree. So how many times you can rotate it to have 60-degree rotations? You can have one, two, three. Three times you will have the same shape while rotating this in a 360 round, right? In a 360 round, you see three times of rotation, right? So in that case, you can call it threefold symmetry. So in this case, you make it two types. I mean, 181 time you have this configuration, and another 180 if you rotate this one, you will have the again the same shape, right? So it's called two-fold. So in a 360 degree rotation, if you see the same shape in two occasions, then you call it two-fold symmetry. If you see three times, you call it three-fold symmetry. In a square like this, you have four sides of similar and 90 degree each in between. So you should have four-fold symmetry. That means each 90 degree you will have the same appearance, right? So it has a four-fold symmetry. If you take a hexagon here as this, you have six similar types of shapes or faces, right? And if you rotate this one, what will happen? Again, every 60 degree, right, rotation, you will see the same shape, but six times, right? So it's called six-fold symmetry. It's called six-fold symmetry in that case, right? So in any case, if any object, if you can see the same configuration at n times, while you are rotating it over a 360 degree, we call it n-fold symmetry, right? N times appearance of the same shape, right? So that is called n-fold symmetry. Okay, so what about one fold then? You have two, three, four, five, six, seven, like that, right? Depending on the shape. But is there anything called one fold symmetry? What is it? One fold. So that means if you rotate an object into 360 degree, you see only one time, right? That means only the original situation. If you come to the original situation only, you see the object. So that means, really speaking, there is no symmetry, right? There is no rotational symmetry. Okay, one fold. There is nothing called one fold symmetry, right? So two-fold, three-fold, four-fold, like that, you can have the symmetry. That means you see the same the object in the same appearance over uh, that particular times, right? Any questions up to here? Do you have any questions up to here? Okay, if anybody did not put the registration number, please put it again. Please put it. I'm reminding again. Right. All right. So these are the symmetric operations and rotational symmetry. Uh, we talked about these three types: reflection or inversion. Sorry, yeah, reflection, like, but it is inversion. It's a different thing, right? We explained how it differs from mirror symmetry, right? Inversion and mirror symmetry are two things, right? Although they look similar to inversion, type of a reflection, right? But it's not real mirror reflection. Okay, in the case of inversion. And then we looked at the rotational symmetry as well. And the other one is the roto inversion. So what was that? Rotation and inversion, both. So you have to rotate the object and you have to inverse it, right? Rotation and inversion, roto inversion. So we'll see what is roto inversion. So in this case, what you want to do is you just rotate the object, right? For example, 90 degree, you rotate it in a 90 degree, and then you do the inversion. Rotation by 90 degree and then inversion. Okay. So you rotate, for example, if you rotate this one 90 degree, right, you will end up with observing this like this, and then you can make it inversion, right? So here you rotate it 90 degree, and then you do the inversion. So this is called roto inversion. It's a two-step operation. It's a two-step operation. You do the rotation and inversion. For example, this one. Uh, See here, this triangle. When you rotate this 90 degree, what you should see. That means you have to make this like this, right? 90 degree rotation, and then you make it inversion, other side. So you will see object like this. For the square also, you see same type of kind of rotation and inversion, right? So it's kind of a mirror plane in two direction. In other words, right? So for example, you can have this shape, and finally you end up with like this, right? So mirror plane, for example, you had this one arrow like this. If you had this one arrow, and finally you will end up with something like this. This is the roto inversion. Okay, so roto inversion is very important because for some crystals uh, that only the roto inversion symmetry is there, right? So this is with respect to a point on, on the axis, right? So ultimately this will end up with uh, a uh, operation which you can describe in a way like this, right? Right, something like this. Okay, so if you make it 90 degree, then for example, right, so I will resolve this out into two phases, two what do you call, two components, right? Two components. How can you make it into two components, right? This is sorry, this is this direction, and you are supposed to have like this, right? Then you apply a mirror plane there. Sorry, not this one, right? Should have the other opposite direction. This one. You rotate 90-degree rotation will not make the arrow shape other way down, right? This is correct, and it should be like this. I'll draw here, right? You rotate this one 90 degree, arrow will not change, and you put a mirror there, right? So then it comes like this. Okay, so it's a rotation and inversion. Rotation and inversion. Okay, so it's like two mirror planes. So here, if you put a mirror plane, you will look, it will look in this shape, right? So that is one mirror plane here, one mirror plane, and the second mirror plane is here. Second mirror plane is here. So that's why you get it somewhere here, right? I will show it again. You have here, and you put a mirror plane like here, right? The same type of shape you should see, and you put another mirror plane there, and you will see like this, right? So originally the object was here, and it moved to this place. This is the roto inversion. So this roto inversion is important when you uh, when you consider uh, the symmetries of some complex crystals, because this symmetrical operation is a bit complicated because you can't at once recognize it, right? So therefore, it makes some complicated crystals. So naturally, you will find some complicated types of crystals as a result of this symmetric operation. So all these symmetric operations are naturally happened in crystals, right? So this that's why we want to make it happen and then understand how it will look like, right? Otherwise, some phases you can't find, you can't figure out how that shape came to that particular crystal. When you look from the upside, uh, it's different, and from the bottom side it's very different. But still, if you apply two types of symmetry operations, then you can generate the bottom shape of the geometric shape of the crystal, right? So this is important. So therefore, you have to understand these basic symmetric operations. Sometimes there can be some combinations, okay? Some combinations can be there, so that will make more difficulties in your uh, identifications, right? So anyway, these are the basic symmetry operations that we have: uh, inversion, mirror symmetry, rotational symmetry, and roto-inversion. So these are roto-inversion is a uh, kind of a combination of two symmetric operations, right? It will look like you put two mirrors and get the shape done, right? It looks as if did like that, okay? Right. Okay, do you have any questions? Do you have any questions? If you have any questions, you can ask right now. We have few minutes. Uh, when you have a look in 3 dimension with some of the crystal shapes which is available at the laboratories, we can have clear understanding about this symmetric operation. So we'll do that as soon as the universities are open. Okay, right. So now then we will stop here for today. We will have the next lecture on next coming Monday. Okay, right.